when the data points are evenly spaced, so we can use the Newton forward or backward difference to interpolate the value of the function at any unknown x. Now, or we can use this forward difference to construct the polynomial, and using the polynomial we can interpolate the value of the function at some unknown x. Now, when the data points are unevenly spaced, that means they are not at xi minus xi plus is not always a constant. When they are unevenly spaced, how to construct the polynomial? For n plus 1 data point, we can find nth degree polynomial. How to construct that nth degree polynomial which passes through all the points? And there are techniques to do that. So first technique, it is an simple technique, but not efficient one. I will say why it is not a good one later on. So let us start with the technique. What is that? Is Lagrange Interpolation. Okay, in Lagrange interpolation, so basically our aim is to construct a polynomial of degree n from these n plus 1 points. In a Lagrange interpolation, let us construct a polynomial pk of x, where k is some index, say from 0, 1, 2, 3 or up to n, any one of index, such that this is equal to the product of I equal to 0 to n, I is not equal to k, x minus xi. So we have constructed, so now you can see, so for n plus 1 points, this will be a nth degree polynomial. So we have constructed, let us construct a polynomial of this form. So k can take the values from 0, 1, 2, 3, only the point you take, the product will go over all i's except I equal to k. So once we construct this polynomial, and we can similarly construct n polynomials, nth degree polynomial by taking k equal to 0, k equal to 1, k equal to 2, k equal to, that's why I can form nth degree polynomial. And then let us say the interpolating polynomial, which is going to pass through all these points, let it be a linear combination of all this nth degree polynomial. That is what, let me say, f of x, that is the polynomial which is going to pass through all these points. Let this be a linear combination, say k equal to 0 to n, some coefficient a of k into pk of x. So, and let this be the polynomial which passes through all the points. So what we have to find here is, we have to find out what is this coefficient ak. So to get the coefficient, let us take, for instance, let us take some xm. So when x is equal to xm, so the interpolating polynomial can be written as, so this will become f of xm, which will be equal to f of m, and that will be equal to summation of k equal to 0 to n, say ak pk of xm. Now if you carefully look at this part, pk of xm, so pk of x is equal to x minus xi, product of xm is only, so only one, it will not have the term, so only what I am saying is, if I write x in the place of x, if you write any xm or anything, so this product will be 0, because there will be all, and if k is not equal to xm, so in the case what I am saying, we are having pk of xm will be equal to 0 if k is not equal to m, or m is not equal to k, whatever it is. Because if k is not equal to m, there will be always one xm minus xm will come out, and that makes it 0. So the entire product goes to 0. So what it says is, so if you want to have pk of xm to be non-zero, the only way is xm should be equal to k. So therefore this will become, So this, even though we have all the summation term, all the products will go to 0. Only the value for which your m will be equal to k, that's the only thing will survive. So what will you have will be f of k, m will be equal to k. So that will give you so that will be ak pk of xk. So from here we can write, so ak will be f of k divided by pk of x of k. So therefore, our interpolating polynomial, when you substitute this ak here, we will get our interpolating polynomial f of x is equal to summation of k equal to 0 to n, and I am going to substitute in the place of ak this one. So this will be pk of x by pk of xk into f of k, or what I am saying is pk of x divided by pk of xk into f of k. So this is a polynomial, and this is a polynomial which can this is a polynomial which passes through all the points, and that won't demand this data point should be evenly spaced. So this was simple. So what happens? So we have to define this product, and so for any x, what you have to do for any x, what happened? So you have to find out this product divided by means for every k equal to 0 and to 0 to n, find out this product divided by this product and multiply by the corresponding f0s. So what you can see is, so if you carefully see, this algorithm is not actually a very good algorithm. Reason is, the interpolating polynomial is summation of n terms, and each term will have a product, n products divided by n product. So you can see the number of arithmetic operations are enormous in this Lagrange interpolation. That's what. So Lagrange interpolation is often not a better algorithm when you particularly have your number of data points are larger. So it will be very round off prone. So that's what it is, not a very good algorithm. But yes, when you have a less number of data points, this gives you a very easy way of finding the polynomial which passes through all the points. Okay, so implementing this algorithm in a program is very simple. It's not very hard. So all you have to find out is these all are just products, and anyway fk, so k goes to 0 to this one, so you'll know what to be done, and so that's it. So this is what the Lagrange interpolation is. And there's another interesting algorithm which uses iterative method, and iteratively it tries to find out the polynomial which passes through all the points, and use that polynomial to find out the function at certain unknown x, and that algorithm is Neville algorithm. What we do in the Neville algorithm is, so let us plot this data point first. So this is our x, and this is our f of x, and we have the data point something like this. It keeps going. For instance, if I give you only one data point and I ask you to interpolate a polynomial using that only one data point, in that case what? The data point is 1. So what is the highest degree polynomial you can construct for one data point is nothing but a constant line, that is degree 0. So this will be the polynomial. So similarly for this point, if I give this point, this will be the polynomial, and you can actually construct a polynomial of degree 0 which passes through all the points. So let us do that. So what am I going to do is, so we have this f0 which is nothing but f of x0. I'm going to write this as a 0th degree polynomial passing through the point x0, and that's a polynomial I have defined. So similarly, f1 will be f of x1, and again it will be 0th degree polynomial passing through the point x1 and this one. So I can keep doing this, and I can get f of n will be equal to f of xn equal to p of n of x. Now what we can do is, okay, so now let me construct a polynomial of degree 1 passing through 2 points. That's what am I going to do. I am going to construct a polynomial which passes through these 2 points, these 2 points, these 2 points, and these 2 points, like that. I'll keep constructing a polynomial which is going to pass through these 2 points. So that will be a polynomial of degree 1. That's nothing but a straight line. So, and am I going to write that polynomial as, so let us write that polynomial as, say, something like p01 of x. So this is the first, this is a degree 1, polynomial of degree 1 passing through the point 0, x0 and x1. So this is nothing but a straight line. Let me write down these values. So this will be x0, f0, x1, f1, x2, f2, and so on. Fine. So we are going to, so this is a polynomial. This is a degree 1 polynomial passing through the point x0, f0 and x1, f1. So this will be nothing but a straight line. So let me write down the equation of a straight line in the determinant form. So that will be 1 minus x1 minus x0 into x minus x0, f0, x minus x1 and f of 1. So this is the equation of a straight line in determinant form. So you can prove for yourself whether it's a straight line or not. That I leave it to you. And so, okay, now we are f0, f1 is nothing but a polynomial of degree 0. So let me replace it. So this will be 1 by x1 minus x0, x minus x0, p0 of x, x minus x1, p1 of x. Okay, so this way I can keep doing it more and more, and I can eventually construct all the lines. So then I can write the polynomial of degree 1 passing through the points x1 and x2 will be 1 by x2 minus x1, x minus x1, x minus x2, p of 1 of x and p2 of x. So we can keep doing this for all the polynomial, final polynomial p of n minus 1 n. We can keep connecting all the points. So now we are going to do a jugglery. So what we did is, so if you see that, so now we had, so what am I going to do? So the same way I keep doing it. That means now what I did is, so initially, so f0 and p0, so basically your y-axis, you are replacing the y-axis with a polynomial of degree 0, and using that you draw a straight line which comes out to be a polynomial of degree 1. That's what we are seeing it here, where p1 and x1 are the points here, right? So this is x0, p0, x1, p1, x2, p2. Now what happened? Let me redefine the axis in terms of the polynomial of degree 1. So then I will draw straight lines. So now that will be a polynomial of degree 2. So what am I going to, what I am telling is, so now let me write down let me construct a polynomial of degree 2 passing through 3 points by assuming it is a straight, you're drawing a straight line when your axis was defined as a polynomial of degree 1. So when the axis is defined as a polynomial of degree 1, if I draw a straight line, so that when it's 2 points, what I'm going to get is a polynomial of degree 2. So that is what? P of 0, 1, 2. That is the polynomial which is going to pass through the point 0, 1 and 2, x0, x1 and x2 of x will be 1 by x2 minus x0, x minus x0, x minus x2, and this will be, I redefine my y-axis as a polynomial of degree 1 that is given by here. So this will be 0.01 of x and 0.12 of x. So this is a way by drawing, again I keep drawing the lines by redefining my y-axis as a polynomial of degree 1. I can do that. So I can keep doing it for more, and what I will do is, so the next line is p of 1, 2, 3, that is a polynomial of degree 2 passing through the points x1, x2 and x3 will be 1 by x3 minus x1 into x minus x1, x minus x3, p of 1, 2 of x, p of 2, 3 of x. So this way we can keep going on, and eventually we can find out the polynomial of degree 2 passing through 3 points. After this, I again redefine my y-axis in terms of the polynomial of degree 2, then again draw the straight line that's going to give me a polynomial of degree 4, and then again I do the same procedure, again draw a straight line there, then again keep again set the polynomial of degree 4 as a y-axis and draw a straight line, you will polynomial of degree 5. That's how you keep on doing it, and finally what you will arrive is, when you finally take out, finally you will arrive as a nth order polynomial which will come out like p of 1, 2, 3 up to n, which is the polynomial passing through all the points, will be a straight line with points xn minus 0, 1, 2, xn minus x0, and that will be passing by an x minus x0, x minus xn, and this will be your y-axis will be a polynomial passing through endpoints. For n plus 1 data, this will be endpoint 0, 1, 2 up to 3 up to n minus 1 time of x, and this will be p1, 2, 3 up to n of x. Okay, so we can keep doing that. So this is how Niville's algorithm is being implemented. So what in Niville's algorithm we do is, we start with the 0 degree polynomial which passing through the points, and then set that polynomial as your y-axis, then draw a straight line which joins, means that's a straight line which joins 2 points. So that will give a polynomial of degree 1, and then once you consider the polynomial of degree 1 passing through all the points, then set your y-axis as the polynomial of degree 1, and then when you again join the two points, set the y as a polynomial of degree 1, so that's going to give a polynomial of degree 3. Keep doing on until you finally get a polynomial which passes through all the points x0 to xn. So this is how Niville's algorithm is implemented. So let us have a look at, let us have an example of how this algorithm is being can be worked out. What we did in Niville algorithm is, okay, so we are having a set of points x0, f0, x1, f1, x2, f2 like xn. So first what we did is, we constructed a polynomial of degree 0 passing through one point. That's what we did. So that we named it as a p0, p1, p2, p3, and then using these 2 points, we construct a polynomial of degree 1 passing through these 2 points, and that's what p01, p12, p23, and then using this we construct the polynomial of passing through 3 points x0, x1, x2, that is here. So this is the p012 is a polynomial which passes through all these 3 points. Similarly, p123 is a polynomial which passes through all these 3 points, and finally p0123 is the is a third degree polynomial which passing through 4 points. So we can keep on going like this in a Nivelles algorithm. Nivelles algorithm iteratively we can do and get a value of the value which is to be value of the function which needs to be interpolated at some unknown x. So let us take an example of this. For example, we have to consider this is a x and this is your f. You can see this is unevenly spaced. So, and this is how the plot looks like. When I plot the data, you can clearly see they are not even, they are unevenly spaced. Suppose you want to find out the value of the function at f of 7.25 for which you do not have a data, that falls somewhere else here in the graph, it falls somewhere else here. So, for this you want to find out the value of the function. So, what we are going to do is, first step is write down the data, and this is the polynomial of degree 0 which is nothing but our f, it starts, and then construct the polynomial which is going to pass through these 2 points. So, that is here. So, remember how to do is you can solve the determinant what we wrote on the board and you can find out. Remember, to solve the determinant you need to know the value of x beforehand. So, Nivelles algorithm, before running you have to give what is the value of x for which you have to find the value of f of find the functional value of the function. So, unlike your Newton forward difference or backward difference, what you have done is you calculated the difference table, forward difference table and the backward difference table and keep it stored in an array, and then you can use it for any x you want to do it, or just all the thing what you have to do is just a summation. On the other hand, in a Nivelles algorithm, you have to, from the beforehand, you have to provide the x, the unknown x for which you have to evaluate the function. So, then you can find out the line, a straight line which is passing using the determinant, you can find out these values, and then again do the determinant, find out this second order polynomial which is passing through the 3 points and keep doing it further, and ultimately you will find out the polynomial nth degree polynomial which passes through n plus 1 point, and that will give you this value. Okay, so this is the value of f, this is the value which corresponds to f of x, what is 7.25. So, if you try to plot that, you will see that falls here, and that is pretty good. It goes closely to the, it follows the trend of other data points. So, this is a very good interpolation algorithm which can be utilized to find out, interpolate for the unknown x. Only thing is, yes, for every x you have to keep doing this entire process again and again. So, computationally this may be again more intensive. So, may not be round off error prone as like Lagrange algorithm, but you may, for if you have to find out your, if you want to interpolate the values, interpolate your function at many x, then you have to repeat the whole process again and again. So, that's what will be computationally intensive one. There is another algorithm which can find out the polynomial when your data points are unevenly spaced, and that basically utilize a matrix, try to construct a system of linear equations and uses matrix techniques to find the polynomial, and so, and that's an interesting algorithm. So, that's what is a Newton divided difference algorithm. So, the task is to construct the polynomial which passes through all the points, and given these points are unevenly spaced, so you can't use this difference as some value, you can't use that. So, given unevenly spaced points, how can I find the polynomial which passing through all the points? So, what earlier method we saw is a Lagrange method, though it can construct, it is round off prone because of the large amount of arithmetic operations you are performing, and Nivelles algorithm is Nivelles algorithm, for you need to provide the x beforehand, and for if you had many x, you may have to repeat the whole procedure again and again. That also, unless until you do some smart way of programming, which I am not aware of, one can do it. So, so that's what Nivelles algorithm have that problem of doing it, repeating it again and again. So interestingly, this algorithm, Newton divided difference, it tries to get to find the polynomial. It converts the problem into a kind of a matrix problem, and we solve it, and then we get the polynomial. Okay, so let us, how to go it, let the polynomial, let us assume, remember all these methods, what we are doing, it's all we are going to get the same polynomial. Okay, because if you have n plus 1 points, we are going to have an nth degree polynomial which passes through all the points. So all these methods is going to give you a same polynomial, but only the difference is how easily you are going to arrive the polynomial. That's how the different algorithm will comes into picture. The Navier algorithm or Lagrange or Newton difference, all are same, but they are unevenly spaced. So let us go with it. So let the polynomial which passes through all the points, let me write it as, so f of x, let it be a0, some constant a0 plus a1 into x minus x0 plus a2 into x minus x0, x minus x1 plus 1. So I can do it up to then, or I can a3 x minus x0, x minus x1, x minus x2 plus, and finally what am I going to write is plus a of n 0 to n and x minus x0, x minus x1, x minus x2 1 up to say x minus xn minus 1. So you can clearly see this is a polynomial of degree n. So this is the polynomial. So if I express the nth degree polynomial passing through all these n plus 1 points as this, and if somehow if I am able to estimate these coefficients such that this polynomial passes through all the points, so then the problem is solved. So what we can, how we are going to do is, let us say our aim is to find this polynomial pass through all the points. Let us say when the polynomial pass through when x is equal to x0, this function f of x0 should be, when x is equal to x0, this will become 0, this all terms will become 0. So what remains is only a0, and which is nothing but f of x0 is f of 0, which is a0. And let us go for the next one, x is equal to x1. So when x is equal to x1, this remains, and this goes to 0, x1 minus x1. So hence all the other terms will have x minus x1, all terms will vanish off. So what you are going to get is f of x1 will be equal to f of 1. This will be a0 plus a1 times x1, because x is x1 now, x1 minus x0. So let us go for one more term, x is equal to x2. So this will be f of x2, and that is nothing but f of 2. So here from this term onwards everything vanishes off. What you are going to get is a0 plus a1, x1 minus x0 plus a2 into x, sorry, this is x2. X is our x2. x2 minus x1, sorry, x2 minus x0 into x2 minus x1. And sub terms will be 0. We can keep doing them. So now if you see here carefully, f0, f1, f2, fn, I can keep doing it for up to x equal to xn. These all are known values. x1 minus x0, x2 minus x0, x2 minus x0, x2 minus x1, these are also can be known values because that's what we are given. What is unknown is a0, a1, a2. So somehow, so what it happens is, if you see here when I write n equations, it is nothing but a system of linear equations, and where your unknowns are a values, coefficients a, and your right hand side vector is f, and the matrix is formed by your the difference in the x values, like that. So if we rewrite this equation in the form of a matrix, how the matrix equation will be looking like is, so let us write this matrix equation. I may need some space, so let me write it a big one. Okay, so first term is A0, 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 they all are A0. So the first column should be always 1. So let me complete this matrix here. And this is unknown vector, and that should be equal to the right side vector. Okay, so the first term should be always A0. So this should be, there's no coefficient for A0, so that should be 1. So this should be A0, and the right hand side will be F0. And for the first, there's no other term, so all these terms will be 0, 0, keep on. Okay, so the first row will contain only 1 and all other terms are 0. And let us go for the second row. Second equation contains A0 and A1, so this will be your A1, and correspondingly here it is F1, and this one will be, of course, first one is A0, second term will be x1 minus x0, and the rest of the terms all will be 0. Let me put it as 0 here. And let's go for the third term, that is equal to A2, and this will be our F2. Of course, it will have A0 term, and then the A1 term will be x2 minus x0, and the A2 term will be x2 minus x0 into x2 minus x1, and then zeros. So what you will see is, when you keep doing that, and here also, so what you will find is, this will eventually form a lower triangular matrix. So this is going to form a lower triangular matrix, and you know how to solve this matrix. For A0 to A1, that's nothing but a forward substitution, which we have seen in our earlier classes. So we can solve for all the coefficients A0, A1 and A2 by solving this this matrix equation. So by using a forward substitution, so once you know A0, A1, A2, and these values are all known, and that will enable you to construct this polynomial. Because consider the polynomial, and given any x, we have already calculated A0, A1 using solving this matrix equation. See, solving this matrix equation, you don't need the x value. All you have to do is provide the data, and this matrix will be solved, and your A coefficients will be already stored. So once you store the coefficients for any arbitrary x for which you need to know the function value, just evaluate this this sum. And well, this is also a very useful algorithm, but to a large extent what happened, okay, you can see these algorithms, your Lagrange, Neville and Newton divided difference, they can interpolate even if your data points are unevenly spaced. So sorry, even if your data points are evenly spaced. So it's not as if they have to unevenly space. Even if it's evenly spaced, these algorithms can be used. However, they are not very simple and trivial. Many of, for example, Lagrange needs a lot of arithmetic operation, those round off prone and all. So most of the times what happened, many times, okay, this is a more efficient algorithm compared to all the other algorithms. Implementation of your Newton forward and backward difference are simpler, and operations are also more or less comparable. So unless until if you don't want to solve this matrix, and if your data points are evenly spaced, it is always stick to Newton forward difference or backward difference, and you can jump down to these algorithms only when your data points are unevenly spaced. So with that, I will stop this polynomial interpolation. So where we try to interpolate the function for any unknown x by representing the data representing the function as a polynomial. And okay, so and what we will do is in the next class we will discuss about the other interesting interpolation, that is spline interpolation, and I will speak about only one spline I will speak, that is about the cubic spline, which is a very commonly used spline. So that we will see it in the next class. Okay.